Very interesting, and maybe good. I think to go back a couple steps in the beginning of your career, because you work with Dr. Michael Persinger, who's famous for the neuroscientist, famous for inventing the God helmet, right? And that was all about electromagnetic stimulation of our brain, which would induce like mystical type experiences. Could you tell us a bit about his work, how it influenced you, and about the God helmet?
Yeah, sure. Working with Dr. Persinger was like a dream come true in grad school, because he was very open to whatever it is that we wanted to study. He was a very open-minded person, but he always emphasized that measurement was very important and quantification was very important. So if you couldn't measure it, if you couldn't count it, or it wasn't subject to inter-observer agreement where we could both point to something and agree, there it is, then it wasn't really within the purview of science. And so he had an open mind, and he studied all sorts of interesting things like mystical experiences and paranormal phenomena and things like this, but always from the perspective of, we are talking about physical systems, we're talking about things that we can measure, and we have to take an empirical approach. So in that setting, we could ask all sorts of interesting questions. And in the context of him having invented this helmet that, really displays the importance of how natural electromagnetic fields can affect the brain, but now in the laboratory context, it was really interesting to take that idea and bring it to the next logical step, which is, well, what is happening to the brain tissues themselves? Is there something about brain tissue that has receptive qualities that allow it to pick up these electromagnetic fields? Is this an ion channel phenomenon, or is this something happening at a different level of analysis? And so we started asking questions, based upon what William James was proposing. And we investigated the claim that the brain has transmissive properties, but we did it in a novel way. Because traditionally in the neurobiological canon, everything that the brain does is really a product of what the brain is generating in and of itself.
Yeah, like this real bottom-up sort of approach.
Exactly, right? Yeah. And it's just a shuffling of chemicals and electrical potentials. That view is really something that is bound to life and living systems. And as long as you have a living system, whatever experiment that you run to try to look for something that isn't based upon that, isn't based upon the productive capacity for the cells to generate these experiences and behaviors, you're always going to have a confounding variable. You're always going to have something that's going to prevent you from drawing conclusions. And so what you want to do is you want to ideally take away the life variable in this analysis. And so we used postmortem brain tissues. These were human brain tissues that had been fixed upon death in formaldehyde-based solutions. And the idea was those brain tissues, which, by the way, when you look at them under the microscope, they have all the preserved brain structure that you'd expect in a living brain. So if you open up the brain, you slice it, look at it under the microscope, you could still see all the cells there. They're all organized in the same way. They're all oriented where they ought to be. All the dendrites and all the very fine filaments are all oriented exactly where they were upon death. But the physiology's gone.
They don't metabolize anymore. Yeah.
They don't metabolize. They don't generate action potentials. They don't do any of the things that you'd expect living tissue to do. Yeah. So what you're left with is a material. And the idea is, if you run current through this material, electrical current, or if you expose this material to an electromagnetic field, how does the tissue process that signal? And it really is a kind of material sciences question. And what we found was when you did that, this was the subject of my doctoral thesis under Dr. Persinger, when you have these tissues exposed to electromagnetic fields in the laboratory that you can control, and you're probing the different areas of the brain, and looking at microvolt fluctuations in those tissues, just how voltage is going up and down. What you find is that the electromagnetic fields that you use are differentially filtered by different areas of the brain. And so it's not acting as this big homogeneous blob. The different areas are still doing different things, much in the same way that you would expect a functional brain to have regional specificity in terms of its function. But this had nothing to do with a living system. It's just a material. So I thought that was interesting. And the thing that really made it for me, the thing that was really sort of the nail in the coffin for me was if you do the same thing that the researchers had done previously, which was to look at geomagnetic activity and to see if, see how patients were responding and look at seizure activity and how that coincides with perturbations of the geomagnetic field. If you did that with the postmortem brain tissues and you just looked at all your experiments that you performed over the past couple years and just retrospectively went and saw, because people record these things, you look at what the geomagnetic activity was like on the days that you were doing the recordings, and you just look at the baseline activity of the tissues, what you find is that the frequencies on the spectrograms, when you actually break down all the different oscillations that are in the voltage fluctuations of the tissue, when you break that down into a spectrum, the spectra are totally different on days of increased geomagnetic activity versus quiet days. And they're within the frequency range that you would expect given that specific area of the brain and what you would expect if it was alive.
Yeah, and so